Okay, off we go. So here's where we left off. So we had been talking about parametric curves and the difference between a parameterization and an equation and stuff like that, right? So the very last thing that I want to entertain in this section before we go on is the idea of how do you find what I'm going to call a point tester for a line in R3. Now you might be thinking, oh, point tester, shouldn't we just write down the equation for the line in R3, right? But the problem is an equation of three variables generically gives you a surface, not a curve, right? So there is no equation, basically asterisk, but basically there is no equation for a line in R3. So what is going to play the role of the point tester? So the big idea here is to just notice that if you parameterize, right, your line, and then if you ask the question, is this point, whatever point I've been given to test, is it on the line? Well, I need to know whether or not there is a value of t that makes that work. So I need to know under what circumstances is there a value of t that works here. Well, now, of course, there's three different equations here. There's sort of the first equation, then there's the kind of the second equation, and then there's sort of the third equation, and you can just solve for t in all three of those equations. When you solve for t in those equations, now again, orange, purple, red, when you solve for t in those three equations, you get these three formulas. Now again, the question is there such a t? Is there a value of t that will make all three of these equations work? So is there a value of t that will make all three of these equations work? And this has become a silly question as follows. Let me make some assumptions about these three expressions. What if, in the scenario that we're considering, what if this one turned out to be 2, and this one turned out to be 4, and this one turned out to be 1? Is there a value of t that makes that work? Well, that's ridiculous. What a preposterous question. T can't be 2 and 4 and 1. It can't. There is no value of t that's equal to these different things. That's, again, goofy. Okay, what if it was 2 and 2 and 6? Again, with the no, right? No, you can't. T is going to have to be one value. That means that all three of these things have to be the same value. These three things have to all be equal. And this is actually a very satisfactory point tester. This is what we call the symmetric equations. If I can get this to cooperate. There we go. This is the symmetric equations for a line in R3, and it serves very nicely as a point tester. And I said there was not an equation. This is two equations. Okay, so that's a nice little tool in various circumstances. Yeah.
Did you just say there's two equations?
Yes. Well, it's two equations, right? Because there's an equal sign and there's an equal sign. Yeah. Right. Exactly. Okay. Moving along. So dot products. I hope you all remember dot products from linear algebra. They're one of the fundamental tools in linear algebra. I hear through the grapevine that at least one linear algebra instructor prefers to call it an inner product, and that's fine, I suppose. In particular, what I call the dot product, and what most multivariable calculus classes call the dot product, is the model for inner products in general. It's where inner products come from. It's the basic default inner product. Okay. So keep that in mind. Make sure you remember all the basic properties of dot products. They're in the book. I'm sure they're in your linear algebra book. I do want to talk about this a little bit. I think this is worth a minute or so. Our book and many others use these two terms, perpendicular and orthogonal, interchangeably. I think that's unfortunate. I'll tell you why. It's because there are two distinct, necessarily distinct, importantly distinct ideas that they both kind of approximately at least refer to, but this is a problem. I mean, approximately is not good enough in many cases. So on the one hand, there's this geometric idea of directions and talking about the angle between them, right? And you have two vectors define two directions, and you can talk about the angle between them. Well, okay, but those better not be the zero vector. If either one of those is the zero vector, there is no direction to even talk about. So this idea, what I call perpendicularity, is a fundamentally geometric idea, and it's for non-zero vectors only. Very important. Okay, now, closely related idea, but not the same, is this little formula right here. Dot product of two vectors being zero. And y'all know that's closely related. Yeah, fine. Okay, but this thing, dot product equals zero, perfectly fine if one of the vectors is the zero vector, or even if both of the vectors are the zero vector. No problem at all, right? So we need a different word for that. Conveniently, we have a different word, and the word is orthogonal. So notice, again, also convenient, this is, I would say, fundamentally not a geometric idea. This is a fundamentally algebraic idea. Check it out. Dot product is defined with algebra. This is an equation. It's an object of algebra. Right? So we have two different ideas that apply in two different areas of math, arguably, to two different collections of vectors, heavily overlapping, of course, and we have two different words with which to describe them. And I think it makes sense to use one for the one and the other for the other, and not to conflate them. So I make every effort to get this right. Now, I'll confess that, as I like to say, I wasn't brought up right on this point. Right? So I have probably 10 or 15 years of, from when I was approximately your age to when I was approximately 10 or 15 years older, during which I was sloppy about this distinction and didn't care. And then I started to realize eventually, oh, that's a problem, right? And so overcoming 10 or 15 years of bad habit is really hard. And to this day, I mess this up sometimes, and I'm sorry. I apologize. You're going to mess it up too, probably, right? So anyway, I think the point is, let's do our best. Let's try to keep this distinction. Let's scoff internally a little bit every time we see someone get it wrong, and just try to make the best distinction we can. Okay. All right. So moving along. Easy, cool fact here. If you have a non-zero vector, and if you want to find the unique unit vector pointing in that direction, unit vector, here's the formula right there. It's easy as that. And the convenient result is you just take the vector you were given and divide by its own magnitude. Nice and simple. Handy dandy little formula. Very important, very useful. We'll be using this a lot. So make extra sure that you know this formula. I also encourage you to make sure you know how to demonstrate that this does what it claims. Right? Persuade yourself that this, in fact, does point in the same direction as B. Persuade yourself further that this is, in fact, a unit vector. How would you prove those facts? Right? So something to think about. Nice little exercise, and again, come and ask me if you have any questions. If you get stuck or whatever. Okay, now next thing we want to talk about component. So a component says, suppose we're looking at some vector W, and suppose that for whatever reason I don't really actually care about the vector W itself. What I care about is the extent to which it points in some direction, and I'm going to describe that direction by way of some other vector that we're going to call V. So V's only job here is to define a direction. What I want to know then is to what extent does W point in that direction? Does that make sense? Easy example, if you should happen to be familiar with American football, if the ball's here and then when the play ends the ball is there, how many yards did you gain? Did you gain this many yards? Nope. Right? If that's downfield and I throw the ball that way and the guy gets tackled immediately, the fact that I threw the ball 15 yards is irrelevant. You're supposed to go that way. And only the extent to which you go that way matters. So in football, only that matters. Okay, so that's just an example. If you don't know football, don't worry about it. Okay, so how are we going to find this component? Before I get ahead of myself, let me acknowledge the component is a scalar. I'm going to loosely say, and I know this is wrong as I'm saying it, but just for intuition purposes, and then we'll fix it in a moment, it's kind of like it's a distance, right? The problem is I can't actually call it a distance because it can be negative. Components absolutely can be negative. And by the way, if the ball, instead of this, right, if it's that, right, if the quarterback gets sacked way back here, that's a loss of yards. Again, it's not about distance being intrinsically positive. It's kind of like a coordinate. It can be positive or negative. Anyway, that's an awkward distinction that we're going to have to always sort of keep in mind. Okay, and with that all said, here's how we compute it. It's actually very straightforward. After all, y'all are experts in trig. That is a right triangle. This is how cosine works. Yada, yada, yada. Good algebra. Make sure you can go through this. This is all just plain old trig, nothing to it, right? And your nice convenient punchline is that this component is computed by that little formula right there. Okay, again, details y'all are going to go through and confirm for yourselves. Now here's an alternative formula, if you like, which I do. We look at this formula that we just derived. And look at this right here. I have V divided by the magnitude of V. It just showed up inadvertently right there in the calculation. V over the magnitude of V, which of course we recognize. That is the unit vector. Yeah, I heard somebody say it. Exactly, right? So that makes for what I think is a much nicer way to think about this formula. Same formula, really, in some sense. But if you write it by taking what in fact is just a unit vector and write it as such, then you get this really nice pithy little phrasing here, which is components are dot products with unit vectors. Rolls off the tongue completely. Pithy is a pretty good word, right? It's very compact. It's very simple. And this is a great way to think about components. Dot product with unit vector, yeah.
So then when going back to find the angle between the components, we could use that in
to find the angle.
Like there's the cosine theta and then the components.
Oh, well, see, cosine was just kind of a means to an end here, right? I mean, there is this angle, right? And I can talk about its cosine. That's true. But really, that was just an excuse for me to get dot product involved.
Right, but could we just do could we use that could we use the new vector times the unit vector in that equation above, or is that different?
The new vector, I'm sorry, I'm not following.
Like at the bottom where you have w dot v, or dot u,
yeah,
can now be applied up there.
This right here?
The same, yeah.
I don't want to. What do you want to do with it? I'm not clear. I'm sorry.
Can it be plugged in up there?
Up here?
Yes.
Oh well, I mean, yeah. But the point is that this is how you compute components. The only reason I wrote this down was because it was a way to get what I want to find on the board so that I can solve for it. Right? So component is not a means for computing cosine theta in most cases, right? Rare circle, I suppose. It could maybe. It could come up. It might be useful. Most of the time, though, the way you're going to compute component is with this formula right here. And if you want to compute the angle, then you would probably typically look at the geometry in a different way. Yeah. So what you say is true, but not particularly useful.
We did that in 201 today, I think. That's what
okay. Yeah. Sure. I'm sure there's some situation where that's useful. Yeah. Yes.
I have a quick question. I don't understand how the cosine disappeared.
Oh, yeah, right. So this is a clever move. You notice that magnitude of V just showed up in the numerator and the denominator out of nothing, right? And it shows up because they cancel. I multiplied and divided by the same thing. It's perfectly legal, right? But having done that, the cool point is that this is the dot product. Yeah. Old formula for dot product.
Yeah. I think I'm so used to seeing like small products.
Yeah. Okay. Yeah. Cool. All right. Yeah. No worries. Okay. Now, related idea. So closely related that it's often confused. But this is an importantly different construction. So now we're going to talk about this thing called the projection. Now, same starting point. We have some vector. We have a direction. That's the only direction we care about. And here, I want to, again, I don't care about the part that's not in this direction. I only want to look at the part of the blue that's in the green direction. The difference being the projection is not a scalar. The projection is the vector that's represented by that leg of this right triangle, for example. Okay, so how would I compute that vector? We've actually already kind of done the heavy lifting on this, because this vector, I already know what direction it points. I already know what its what its magnitude is. Okay, apologies, because the magnitude, I know what the component is. Right, I know how to compute components. Components, though, might not be positive. Magnitudes are positive. So there's that little awkwardness, and I apologies. But that little awkwardness aside, it's very convenient to say, well, let's start off by presuming the component is positive. Then the component is the magnitude of this vector. And if you know the direction and the magnitude of a vector, then you can easily realize that vector as being the unit vector representing the direction times the scalar representing the magnitude. Direction and magnitude. That's what a vector is. Right. So, there you go. There's our formula. And I guess we can rewrite the component, of course, as a dot product with a unit vector. Right, there's that little convenient phrasing. Component is a dot product with a unit vector. And we have ourselves a handy formula for the projection. Right there, like so. All right. Again, can't emphasize enough. This is a vector, not a scalar. Okay, now let's entertain real quick what happens if the component actually is negative, right? What if this vector here were like that, pointing in the, ultimately in the wrong direction, right? Again, what if the quarterback gets sacked, right? Then the component will be negative, and the projection ought to be in the backwards direction also. So perfect, right? In fact, it's not awkward that the component is not a magnitude. It shouldn't be the magnitude. The fact that it could be negative sometimes is exactly what we need. So, Andy. All right. Now let's talk about this formula. Is this a good formula to use? Here is an alternative. Let's see here. Do like this. And all I'm going to do is recognize that this unit vector is v divided by the magnitude of v, right? There's our old little handy formula we just talked about on the previous page. What happens if I multiply this all out? Well, notice, and again, details for y'all, it turns into this. So which formula do we like better? Do we like this one or do we like that one? And I'm going to give you some pros and cons to think about. Let's start with devil's advocate. I'm going to make the case for the one I ultimately don't like as well. This formula does have a redeeming feature because the question was to compute the projection of W in the direction of V. W and V are given. This formula is in terms of W and V. It's very plug and chug. That's nice. And if you have to actually do the plug-in and the chug-in, you'll appreciate the fact that it's plug and chug friendly. That's nice. Okay. Now let me make the case against it. While, yeah, you might have to plug and chug a little bit, maybe a few times. In practice, computers are going to do that for you in practice most of the time. This is not a big worry. On the other hand, this formula is hard to remember. Dot products and W's and V's, and there's a lot going on here, right? Why is this scalar out in front, what it is, and why is this intuitively obvious? I can't make a good case for that. I can make a great case for this. That's a direction, that's a component. This is what I'm going to call natural. It's conceptually convenient. It's conceptually transparent. I couldn't forget this if I tried. This I'm going to forget in the next 15 minutes. And I won't be, oh, guys, is it the W's with the V's, or is it the which is on the denominator? Is it the W or the V? And it's easy to get it backwards, right? So for your consideration, I think this is the most important formula to know, the one up here on top. That's the one that actually makes sense. Keep in mind what we do here, right? Our job in this class is to connect ideas with other ideas. That's what this does. This doesn't really so much. So if I were taking this class, if I were an undergrad again, taking this class, I'd probably go ahead and make sure I knew both right before the test, right? But I would be putting all my marbles onto this one, and then, maybe right before the test, I'd make sure to know that formula. But might as well know both. Couldn't hurt, I suppose. But that's the most important one. Okay. All right, last comment on 1.3, and that is vector algebra can be useful for proving certain facts about high school geometry. And there's some cool examples of this. The book has 2 nice examples, and I encourage you to take a look at those. It's pretty straight read. I don't think you need me to, there's no deep water there for me to comment on, so I'm going to let y'all read those yourselves. There is at least one homework exercise that's kind of along those lines. The important thing, I get 2 seconds. The important thing that I will point out is when you're setting up one of these arguments, make sure that you are crisply clear as to what the objects in your argument are in your picture. Right? It's tempting to not label enough things and give names to enough things. That's a stumbling block for a lot of students. So anyway, read those examples, keep that point in mind, and you'll be all good. Yes?
Yeah, so I've heard the projection described as a shadow before. So,
kind of.
Just to clarify, can the projection be longer than the component it's projecting onto? Not
in Euclidean geometry.
Okay.
Yeah, right. Because, triangle. Right? Here's your original vector. It's a hypotenuse. Here's your projection. It's a leg, not a hypotenuse. So it just not going to work out. Okay. So it is a kind of a shadow, but it's not fair to say that every shadow can be thought of as a projection, right? So at 10 seconds before sunset, my shadow is 5 miles long. right? And but that kind of a shadow is not relevant to projections. Yep, right. Okay. All righty, so that's 1.3, off to 1.4. Two things to say about this. First of all, there are a lot of different ways to present the material of section 1.4. There are pros and cons to every different way to do this. The reason for that is that there are a bunch of ideas that are connected in even more different ways. Right? So this is not the ideas and the connections between them in section 1.4, it's not like there's kind of a line of ideas and the connections just are like that and it's just, this is the collection of ideas. No, the collection of ideas are like my fingertips and the connections between them is this sort of, hairball of complexity of lots and lots of connections between these ideas. So lots of different points of view, lots of different ways to present these ideas. The book makes a very reasonable choice on how to go through these ideas, what order to present the ideas, and how to draw those connections. I'm going to do something that's significantly different because ultimately I think mine avoids a lot of the ugly. There's a lot of tedium in the book's approach. The order that I'm going to do the ideas here is less rigorous. That's the downside of my approach. But it's geometrically pretty satisfying. A little bit of algebra, not that much, not so bad. But it's algebraically much more convenient. I think it's geometrically much more satisfying. I think you'll like my approach better than the books. But, we'll see. Okay, so I'm going to start off with this idea of geometric order of a list. We'll start off by talking about a list. What is a list? It's like this. It's kind of like a collection, but the order matters. In a list, the order matters, right? Which one is first, which one is second, is part of what is a list. Okay. All right. So here's a list. A first, B second. I'm going to kind of draw an arrow there just as in recognition that A is first, B is second. And now let's think about what these vectors look like geometrically. A might be, for example, a vector like this, and B might be a vector like this. And now let's think about, from the point of view of this geometry, looking at these actual vectors. If A is first and B is second, I think it makes sense to call that a counterclockwise list. You know what I mean? Now, on the other hand, it could have been, again, A first, B second. Let's suppose that was the A vector. Now, it's a different vector. Right? And let's suppose that is the B vector. Again, a different vector. But if I stick with A first, B second, A first, B second, I think it would make sense to call this a clockwise list. Everybody see what I'm talking about? Yeah.
Could the image on the left still be a clockwise? Like if you just
I hear what you're saying because like this.
Yeah.
So always go in the shortest possible. Yeah. So that's much longer than this is. So we always want to go in what I'm going to call the obvious direction. Yeah.
Got it.
Yeah. Okay. All right. So this is what we mean by clockwise list and counterclockwise list. Notice this is when I have two vectors in two dimensions. Okay. There are these anomalous sort of third scenario cases. Like you think about this here, A, B, as indicated here. Well, you don't really go either direction. It's not clockwise, not counterclockwise. Likewise, if A was 0. Likewise, if A was backwards of B. Right? There's various different versions. What if they were both 0? What you're going to notice quickly is all the failures of using clockwise and counterclockwise, they are all linearly dependent. And that's a good little exercise to think through. Think through all the different geometric sort of versions of neither of those working. They're all linearly dependent. Okay. So, this is not deep water, right? It's a pretty straightforward idea. These ideas of clockwise and counterclockwise, I think it's a pretty easy pitch that counterclockwise and clockwise are mirror images of each other. Right? Not too surprising to suggest that if you trade the positions, in other words, if you look at A first, B second, versus if you look at B first, A second, right? If you change where the vectors are in the list, that'll change the order. This turns counterclockwise into clockwise. Okay. And then lastly, if you rotate the entire picture, so here I have A, B being counterclockwise. If I take this whole thing, this whole picture, and rotate the whole thing counterclockwise by some amount or whatever, rotate it any way you want. Counterclockwise remains counterclockwise, right? These resulting vectors still counterclockwise. Is that satisfying? Okay. Again, not too shocking of a result. Now here's where it gets a little weird. What if we wanted to do a three-dimensional version of this? What is a three-dimensional version of clockwise, counterclockwise? And this is not immediately obvious how we would do it, but it's pretty satisfying once you see it. If you have three vectors in R3 in your list, you can use the human hand. So here's the way this works. There is a particular hand gesture that was established a long time ago and has been pretty much universally agreed upon, and we're all doing the same thing. It's somebody made this up, but it's handy, so we're just to be consistent. Everyone's going to do the same thing. Here's the hand gesture. The idea is that your index finger has to stay parallel to your palm. Your middle finger bends the way middle fingers want to bend. Don't get cute, right? So just bend the middle finger the way it kind of wants to. And then again with the thumb, just kind of don't break your thumb or whatever, right? So this hand gesture right here, and you can do it with your left hand as well. Right? Does everybody see the hand gesture? Okay. The index finger is first. The middle finger is second. The thumb is third. Again, arbitrary. Again, standard. Claim this is a right-handed list right here because A, first vector, first finger, index finger. B, second vector, middle finger is the second vector. And then check it out, my thumb can totally point in that C direction. Everybody good? Okay. Now I can try to do this with my left hand. Oh, let's see, how am I going to? Okay, all right. So I can point my left hand index finger in the direction of A, and it looks like I'm in trouble with B, but not really. Look at this. I can go sideways. Now I can point my middle finger in the direction of B. So I got the A and I got the B, index first, middle finger second. But now my thumb is pointing the wrong way, not the right way. So this is not left-handed. It is right-handed. Everybody good? All right. Okay, now a little bit of a clarification, kind of a detail point. Notice that the first two vectors A and B, define a plane. There are limits to how flexible my thumb is, right? So if this C vector, for example, were pointing back that way, my thumb doesn't do that. It's just not that flexible. But a refinement of the rule is index in the direction of the first vector, middle in the direction of the second vector. Notice now, taking a pause, that defines this plane. And notice that your thumb points on a well-defined side of the plane. And as long as C is on the same side of the plane as your thumb, that's okay. That's still right-hand order. Okay, you can try the same sort of thing with this trio of vectors over here. And again, A first, B second, C third. And if I try to do this with my right hand, I fail. But I can 100% do it with my left hand. Yeah? All right, and again, it's going to fail sometimes. Again, sometimes C is not on either side of the plane. In this case, C is actually parallel to the exact same plane. So, again, fail. Or what if one of the vectors was 0? Or what if two of the vectors were parallel? What if A and B were parallel? All sorts of failures. Any failure, you'll notice, is linearly dependent. Okay, so we see a pretty strong analogy already. These are geometrically natural choices that are kind of opposites of each other in some sense, where every scenario of a list of three vectors is one or the other or dependent. Pretty analogous. And the analogies just keep on coming. Look at this. They've got these same three properties. They're mirror images of each other. Right hands and left hands are mirror images of each other, just like clockwise, counterclockwise. If you trade the position of two of the vectors, that changes the order. So A, B, C. Let's see what I got with my right hand here. A first, B second, C third. A, B, C is right-hand order. But if I switch the order of two of the vectors, and now notice I've kind of traded the A with the B there. If I make that switch, and now say, what if B is first, then A is second, and C is third? Left-hand order. Right? So this is always going to. Anytime you trade the positions of any two vectors in the list, the handedness will change. And then again, independent of rotations. And again, this is, I think, pretty geometrically satisfying. Here's a right-hand order. If I rotate the whole picture, still right-hand order because it's still my right hand. So pretty believable. So bonkers analogy, right? Right hand, left hand has the exact same, analogous same three properties that clockwise, counterclockwise have. Okay. All right, now there is a fourth property. There is kind of no two-dimensional version of this particularly. It's this idea of cycling the list of vectors. Cycling means that every vector in the list, you kind of move it over one spot in the position in the list. You just kind of keep everything just shoves over by one spot, and then of course A falls off, and then you put it back on the other side where there's a new opening. Right. So this is called cycling, and I claim cycling always preserves order. So if you have a right hand list, as this is, let's see here. That's a right-hand list, A, B, C, right? Then BCA is also right-handed. Let's see here. There you go. BCA. Everybody see that? Okay. All right. Okay, always works, yes.
In the previous slide, in the order is independent of rotation.
Yep.
What does the R mean?
This just means a rotation. So some sort of a rotation. I'm going to take the A, B, and the C. I'm going to rotate each of A, B, and C in exactly the same way. So that's what I'm doing here. Right, so that's a rotation. And as long as you rotate all the vectors exactly the same way, then the images will have the same handedness as the original list. Yeah, right. Okay, some old theorems that you may have seen. These are really cool theorems, really important theorems, really surprising theorems. And I'll bet you've seen at least part of these theorems before, and I'll bet you also that you haven't seen everything about these theorems that I'm about to show you. There's a lot of setup that goes into these theorems, so bear with me for a minute. Everything that you can see on the screen right now isn't even the statement of the theorem. We're just setting up the statement, which we haven't even gotten to yet. So anyway, here we go. Let's do the setup. Suppose you have a list. 2 vectors in R2. Given a list, you can make a matrix. In the what I'm going to call the sort of the obvious way, the first vector you make it the first column, and the second vector you make it the second column. Now that's arbitrary, but it's pretty natural, right? So nothing particularly creepy or weird about that. So you give me a list, I can make a matrix. Now, if you give me a matrix, I can make a linear transformation in the usual way. A linear transformation, of course, is a function. It has a domain and a target. Given the specifics that we're dealing with here, that's a 2x2 matrix. So this is a function from R2 to R2. Now, again, I haven't said anything yet. You gave me a list. From that, I make a matrix. From that, I make a linear transformation. So what? Still not done with the setup. There's one more thing I need to make. And again, I think this is pretty natural. Once you have a linear transformation, you can ask, hey, what's the image of the unit square? Let's take the unit square here, put all these points in the unit square into the linear transformation, and let's see what comes out. And I claim it is a parallelogram, generically. I mean, it might be squished or something, but anyway, most of the time, generically, it's a parallelogram. Yes?
We would have to be given the transformation.
Well, we'd have to be given the list, but once you give me a list, I make a matrix. Once I've got a matrix, then this gives me the transformation. All this comes out of the list.
But what about the x? Like, how would we...
Well, this is so this is a function. So t is a function, and the way you describe a function is by what it does to arbitrary inputs.
But we would be given the function.
X is a dummy variable. So no, you're not given t. We're generating t. Right? If from the list I write down the matrix, and given this matrix, that defines this function. Okay. And then this function is something you can do to any vector x.
Okay.
Is that cool?
Yeah.
Yeah. Yes.
So once you generate the function, the t, then we multiply the matrix and the vector x. Right?
Yeah, this is just kind of our standard relationship between matrices and linear transformations. Mm-hmm. Whenever you have a matrix, you could write down this expression that is a function, and in fact, it's always a linear transformation.
And so how is that related to the p?
To p? Well, yeah, because once you have a linear transformation, I can ask what happens when I take the unit square and plug all those points into the transformation, and if you look at what comes out, you always get a parallelogram.
So now instead of having the input variable as vector x, it becomes s.
Well, yeah, I'm going to take all of the points of S, right? All of the points that are inside of S, one at a time. I'm going to take all those points and put them into this function and see what comes out.
Okay.
Yeah, cool. Okay, all right. So now we've got a setup. Now I'm actually going to make a statement, right? A conclusion. With all of this setup, amazing fact. The absolute value of the determinant is the area of that parallelogram. It's really weird. It's really surprising. It's also really suspicious. I mean, I'll point out determinant is 3-function arithmetic. Multiplying and adding. maybe subtracting. There's not even division. Easy, trivial arithmetic. How else would I compute this area? Well, I'd drop a perpendicular and compute that with some trig based on that magnitude, which has a square root in it, and multiply by the length of the base, which has another square root in it. There's ugly algebra that goes into computing this area by classical high school methods. Square roots and trig. Yikes. And I'm saying, no, you can do it with three-function arithmetic. Seems a little too good to be true. Know what I mean? Okay, now you may have seen that before. I think most students have probably seen that before. Here's a take that you might not have seen before. I think most of you probably not. And that is, rather than thinking of this as a statement about the parallelogram, I want to interpret this as a statement about the transformation. This absolute value of the determinant is telling me something very important about this linear transformation, as follows. The transformation here started with an object whose area was 1, and then it produced an object whose area was that absolute value of the determinant. So this transformation stretched areas by a factor that is this absolute value of the determinant. So you can think of this absolute value of the determinant as being a static area of a single thing. Or you can think of it as a factor that this active linear transformation does to any areas. And that's conceptually a very different point of view, and in certain moments that's actually really important and really useful. Yeah.
So if, for example, S had an area of like 2,
yep, and
the determinant was like, I don't know, 5,
yep,
would that mean P would be 10?
Yep, that's right.
The area scale factor.
Yep. Whatever. If you have a linear transformation comes from a matrix, and if you have some input area and some output area, this factor is the factor that the area stretches by. Absolutely. Yep. Yes.
So S and P, in terms of just like what object they are, would they be represented as matrices?
No, these are just sets.
Okay.
So this is just a unit square. This is a parallelogram. But I claim that this works for any areas. This is, again, fundamentally telling us something about T. Now, there's another thing that we can conclude. This is a shocking, arguably even weirder result. Let me shrink so I can fit this all on here. So, looking now not at the absolute value of the determinant, but looking at the sign of the determinant, plus or minus. That tells me about the order of the list. That tells me if this list is clockwise or counterclockwise. It's a little unexpected, right? But see, you don't have to take the vectors A and B and like plot them and see which directions they point and think about what your alternative. No, you don't have to do that at all. You just look at the determinant, see if it's plus or minus. Plus means counterclockwise. Minus means clockwise. And here's another wild take on this that I doubt you've seen. Well, some of you, who knows? But many of you have probably not seen. Notice that if we look at, and I'm going to clean up my picture here a little bit. Oh gosh. Here we go. Keep in mind we've got E1 right there. And we've got E2 right there. And let's think for a moment, what are the images of these vectors? If I take E1 and pop it into T, what comes out? Well, E1, when you put it into T, I'm going to be multiplying A times E1. That's going to give me the first column, which is the first vector, which is this edge. And likewise, the image of E2 is that edge. And so here's the cool thing. As drawn here, notice the counterclockwise E1, E2 has turned into counterclockwise AB. Now what does that mean? What does that tell us about this linear transformation? And short version, there's definitely not any flip happening here, right? If there was inside of T, if there was a flip, if there was a reflection of any sort of inversion, depending on how you want to think about it, right? Flipping things upside down would turn counterclockwise into clockwise. If the sign of the determinant is positive, and that means that this list right here is counterclockwise, E1, E2 is always counterclockwise, that means T has no flip. And if it went the other way, and of course my picture wasn't drawn this way, but if A and B had been, the other way instead, then counterclockwise would have turned into clockwise, which would mean T has to have some sort of a flip or reflection, some kind of an inversion hidden inside of it somewhere. It's turning R2 upside down. So again, you can think about the plus or the minus as telling you something about the list, or you can think of the plus or minus as telling you something about the linear transformation. And in some circumstances, that's what's really the most useful thing. And then let's see, I'm out of time. But I do want to point out the three-dimensional version's exactly the same thing. 3 vectors in 3 space makes a 3x3 matrix, which makes a transformation from 3 dimensions to 3 dimensions, and the determinant's magnitude gives you the volume. The plus or minus tells you if there's a flip. Okay, gotta go. See y'all later. Y'all have a good one. Have a great weekend. Oh, and I owe y'all an email about the homeworks and grade scope and all that, and I'll be sending that before I leave today. See you later. Give me 2 seconds. Let's see, I just gotta click the quit here.